In the last lecture, lecture 10, we have seen from phasor diagram how could we draw the impedance triangle. So now here in this lecture we will know that how could we derive the resonance for a circuit from the impedance triangle. So this is the impedance triangle, and from there we have derived the equation for impedance, that is Z equals to root over R square plus XL minus XC whole square. In that case we have considered XL is greater than that of XC. That's why VLT is greater than that of VCT. But now let's consider XL equals to XC. That means inductive reactance equals to capacitive reactance. So in that case XL minus XC equals to 0. That's why Z equals to R. Here a phasor diagram has been given which has been considered for RLC series circuit. So here it is clear that although the circuit is having R, L and C, that means their individual impedances are resistance R, inductive reactance XL and capacitive reactance XC. So although these impedances are available in the circuit, but as we have considered XL equals to XC, that's why these two opposite phasors VLT and VCT are equal to each other. So these two vectors will cancel each other. So only resistive component is available in the circuit. Okay, so this is the resonance condition. That means XL equals to XC. So in that case we can say that the circuit is having only the resistive component. So impedance Z is equal to R. That means whenever the circuit is purely resistive in nature, at that time we can say that the circuit is at resonance. Since XL minus XC equals to 0, that's why we can say that impedance is minimum in that case. So whenever resonance is occurred, at that time impedance is minimum. So as impedance is minimum, we can say that current is maximum. As Z equals to R, that's why power factor cos phi equals to R by Z equals to R by R, that is 1. So power factor is unit. So it is known as unity power factor. So we can define the resonance in this manner that whenever power factor of a circuit is unity, at that time we can say that circuit is at resonance. Thus at RLC series resonance, impedance is minimum, therefore current is maximum and power factor is unity. At resonance, as XL equals to XC, that's why we can write omega L equal to 1 by omega C, and from there we can get the resonance frequency of series RLC circuit Fs equals to 1 by 2 pi root over LC. Resonance is frequency dependent, and at resonance circuit is purely resistive in nature. Q factor or quality factor is the ratio of reactance to resistance of the circuit. Thus Q equals to omega L by R or 1 by R omega C. Actually, Q factor shows the selectivity of the circuit. Q equals to omega L by R. Again, omega equals to 1 by root LC. Thus, Q equals to 1 by R into root over L by C. As Q inversely proportional to the R, that's why with the increase in resistance, quality factor of inductor is reduced. That is shown by the graphical representation. Here we have considered frequency versus current graph. So at resonance frequency, the current is maximum. So three graphs have been considered here, and the amplitude of the maximum current graph is reduced with the increase in resistance. That means the selectivity will also be reduced with the increase in resistance. Actually, selectivity is the sharpness of the curve. Now, resonance in RLC parallel circuit. The circuit is shown here where current IT is divided in three branches and its corresponding current phasor diagram has been drawn here. Let's consider ILT is greater than that of ICT. Thus, resultant vector is ILT minus ICT. Here, RIT is in phase with the voltage VT. Capacitor current ICT leads the voltage VT by 90 degree and inductor current ILT lags the voltage VT by 90 degree. Thus, there is a formation of current triangle. From this current triangle, we can write this equation. Therefore, this equation can be derived. Since at resonance XL equals to XC, that's why Z equals to R. That is the condition for resonance in RLC parallel circuit. Since the circuit is parallel, that's why its impedance will be maximum whenever resonance is occurred. Therefore, its current will be minimum. There is a current versus frequency graph, and at resonance frequency, it is seen that current is minimum. In that case, quality factor Q is equal to R into root over C by L.